Yeah. So it's all clear, no other questions? Good. So it seems that this year there are, last year I covered here more others. People were, I hope that what stopped me is the so the next topic is norms, right? It's a very important notion that can be applied to vector and matrices. Most commonly to vectors. So what is a norm? There is a function which measures the length, so to speak, of the vector. We measure the length. And it satisfies this. So the function which takes a vector and associates with the vector a non-negative number. Right? So the range of the function is a negative surface. And satisfies these three following properties. So it's more or equal than 0, as I said, but also whenever it is equal to 0, then x must be equal to 0. Okay? This is the first requirement. Second requirement, which is called the triangle inequality, is that the norm of x plus y is less or equal than the sum of norms of the y. Okay? And the third property is that if you take a vector and you multiply it by a scalar, right, by a real number, the norm of the scale vector is equal to the product between the absolute value of the scalar times the norm of x. Okay. So if you think about it, the norm is exactly the function that you would use to measure the length of vectors in the plane. Right? Vectors in the plane, let's call it x, y, right? And the length of these two vectors is more than 0, and they are not the origin, right? And they are not the length. And if you sum the vector up, you obtain another vector in space, right? You can compute geometrically by the parallelogram vector position x plus y. Now the norm of this new vector is less or equal than the sum. The length of this vector is less or equal than the sum of the length of the vector. Likewise, if you take x and you multiply by 0.5, you obtain this vector. This length is the length of x. But in general, a norm is a function which satisfies this property, but does not need to measure exactly the length of the vector, as I said here. So the length of the vector is a special case of a norm. And there are many more. We'll discuss some of them. So there is one more property before we discuss some examples, which is very important. One more property of norms is that they are convex functions. So we discuss convex functions, convex sets later on in the course, because another topic which is very important is occurs frequently in machine learning statistics. But so let's just recall that the function is convex is if every time you take a convex combination of two vectors in the domain, so you take x and y, you take a convex combination. So there's a convex combination, you multiply x times lambda and y times 1 minus lambda, and lambda is a number between 0 and 1, right? Okay. So what this means, going back to the previous example, we have x and y, right? And if you let lambda varies between 0 and 1, so when lambda is 0, you have y, so you have this point. When lambda is 1, you have x. And when lambda varies between 0 and 1, you can take any point on the line segment joining x and y. Right? Now what happens is that the norm of a convex combination of x and y is, so the norm is convex, which means that the norm of a convex combination is less or equal to lambda times the norm of x plus 1 minus lambda, the norm of y. And this is true because of the properties, right?
Yes. What's the convex combination? Can you explain that?
The convex combination is this way.
Yeah.
The set of all vectors which are obtained by taking a combination of x and y with a coefficient which are non-negative and sum to 1. So the first coefficient is lambda, and the second is 1 minus lambda. So the norm of a convex combination is less or equal than lambda times the norm of the first vector plus 1 minus lambda the norm of the second vector, which is exactly the definition of a function being convex. This inequality is true because the way you see it, let's say it is in detail. So you apply first the triangle inequality, right? So, right? So the norm of lambda x and y. So this norm is less or equal than the norm of lambda x, the first vector, plus the norm of 1 minus lambda y. Right? So this is the second property of a norm, second requirement, the second bullet point, the previous slide. And then you use the third property, which is called the homogeneity property. Right? The norm is a one homogeneous function, which means that at the time you take the norm of the vector times the scalar, you can take the scalar out of the norm and put the absolute value. So then it is equal to lambda, absolute value of lambda is lambda, because negative times x. So you apply the homogeneity property here, then you apply here, 1 minus lambda, again negative, times the norm. So the norm is a convex function. And this is very important. For example, those of you who were yesterday in supervised learning, you take the square norm, right? That is used as a regularizer in regularizing squares. So it's a convex function. The special case of a convex function. This, using convex function, ensures that when you search for the minimum of the function, it is equal. The function is convex. You can design some algorithm which, looking at the function step by step, converge the minimum of the function. Here is the same. So understanding the property of norms is important, for example, for designing learning algorithms. So what is an example of a norm which is not a Euclidean norm? The Euclidean norm is the length of the vector. These are P norms. So here P is any number which is more or equal than 1. So the P norm is defined by these formula. We first take the the sum of the p power of the absolute value of the component of the vector, and then you take the p root. Okay? So if p is equal to 2, we have the Euclidean norm, right? The square root of the inner product, we have defined before. Right? So p equal to 2, take the sum, 1 to m, xi squared, we need to put the absolute value square, and then you take the root. So the inner product of x with itself, square root. This is the length of the vector. But, for example, if p is equal to 1, you take the Elmer norm, and this is the sum of the absolute values. But turns out, we need to prove it, that this is a norm. Okay? And the sum of the absolute values of the vector satisfies the three properties which make a norm, which make a function be a norm. So it's kind of intuitive. Negative, the sum of values. And if it is 0, it must be the case of all the components of x are equal to 0. Right? That's also clear. And it satisfies the triangular inequality. Right? The absolute value of the sum of two numbers is less or equal to the sum of the absolute values. And it's clearly this is homogeneous. If you multiply all the components of x by a number, the norm is multiplied by the absolute value of the number. So if you think about it, you see that it is a norm. Now what is interesting, this norm is bigger than the clear norm, right? Because the sum. So what is this norm? It's the sum of the length of the chord. If you are in two dimension, take the vector x, okay, x1, x2. And these are also two vectors, they have a multiple of the x and y, the first axis and the second axis. Do you say axis or axis? Axis. 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 Singular. One axis to axis. 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 So, clearly, the length of the vector is smaller than the sum of the length of the sum of the absolute value of the coordinates. Right? The coordinates can also be the components of the vectors. The components of the vector can also be interpreted as an horizontal vector and vertical vector. We know from the Greeks that it used to be. So, what is the other interesting norm? So the challenge is to show that this is a norm for every p. Let's show it. The other interesting case is when p goes to infinity. So when p goes to infinity, you obtain this function. Show it. So take the maximum of the absolute value of the components. This is also a norm, and it's called the max norm. Now there is a norm which I forgot. It's called the metropolis. The metropolis distance. Who knows what the metropolis is?
It's just the sum of the.
Yes.
The distance.
Yes, exactly. So if you are in New York and you want to go to the shop of the vectors, you have to go there and so on. So that's the N1. Okay. Yes. So norms are also also induce distances. So if you take two vectors, right? You take the norm of the difference, that's the distance from one vector to the other. So the L1 norm induces the metropolis distance. Right? Whereas the L infinity norm, with the max norm, okay, also more than infinity, we measure the distance between 2 points as the maximum of the two components. So this norm is smaller than the L1 norm and the L2 norm, right? Because you only take the largest component of the vector. So why is this norm? And again, if you think about it, you see it satisfies the 3 properties. Right? It's more than 0. If it is 0, it must be the case that the vector has always component equal to 0. What about the triangle inequality? That works, right? So, and let's take a moment. The third property, the homogeneity property, is also clear. If you multiply all the components of x by a scalar, right, the maximum of the absolute value of the 5 vectors is still equal to lambda times the maximum component. Now, about the second property, triangle inequality, so we need to show that the maximum over I of xi plus yi, these are the vectors, right, is less or equal than the maximum over I of xi plus the maximum over I of yi. Right? That's what the triangle inequality says. Right? The norm of the sum of two vectors, which is the maximum of the absolute value ith component of the formed vector, right, is less or equal than maximum absolute value for the component of x plus the maximum absolute value for the y. This is true simply because the absolute value of the sum is less or equal than the sum of absolute values, and then the maximum sum is equal to the sum of maximum. It's less or equal to the sum of maximum, so this goes. So this you need to think a little bit about. All the, I would say that it's a bit more difficult than the other group we made in L1. So you have norm for vectors, but you can apply norms also to matrices. And you can do it in 2 ways. So the first way is kind of straightforward, in the sense that matrices can also be taught as vectors, right? So you just take the columns of the matrix and you stack them one after the other. You have a big vector, right? That's a different, not default way to represent a matrix. Just represent it as a big vector, or perhaps you can stack the column one after the other row-wise. So you have a vector which is n times n, a big vector, and then given this big vector, you can reconstruct the matrix by taking the first n element, the second n, and so on. So it's clear that matrices form a vector space. So you can sum matrices, you can multiply them by scalars. You can think of a space of n times n matrices as a n times n dimensional vector space. So you can think of you can define a previous norm also for matrices, right? We will see them here. exactly the same definition that we've seen before applies to matrices. You just have a bigger vector which is as a double index. It is exactly the same thing. Just the notation changes and perhaps confuses a little bit, but the concept is the same. However, in the case of matrices, you can define a special class of norms, which are induced matrix norms, which are peculiar matrices. Okay? You can define them because your object is not just an element of a vector space as a matrix is, but it is a matrix. It's an object which has rows and columns, its elements have a double index. And here, the way you define the norm is by thinking of A as a linear transformation. So it's defined by this equation. And this is that's a bit more abstract. I'm not able to give perhaps the method interpretation. It's the form of the interpretation. But then you take, you form these ratios. You apply A, you transform X with A. X is an arbitrary vector in the domain space Rn, right? And you take the norm of the image of X, right? So Ax. This is a vector in the m-dimensional space. For this reason, I put here n, right? So you need to have two norms: a norm for the range space and a norm for the domain space. Okay. So the norm for on X is denoted by n. We always keep n there, parentheses, and the norm in the domain is denoted by m. We have two norms, like one could be one norm, the other could be the max norm, or they could both be the Euclidean norm, p equal to 2 in this definition. So you form this ratio, the ratio of the norm of Ax divided by the norm of X. Okay? And again, it's important these are two vectors of different length, and you use two different norms. And then you let X vary, and you see what is the maximum that this quantity can take. Right? And that is the norm, the induced matrix norm. The norm induced of A, which is induced by choosing a norm for the domain and a norm for the domain. Now, since the way you construct this is by taking two norms, you can show that this is also a norm that satisfies our three properties, our three conditions for a function being a norm. Right? Well, first of all, since you take the supremum of numbers which are more or equal than 0, the norm will be more or equal than 0. Then, if the supremum is equal to 0, it must be the case that A is equal to 0. So the first property is satisfied. Right? So if A is different from 0, the supremum will be more than 0. Right? So if A is different from 0, it means that there is a vector X such that E of X is different from 0. Then the third property, the homogeneity property, which I put here lambda, alpha, and I'm sure this is equal to absolute value of alpha times the norm. That's also true because you apply the property here, in the case of this norm, you take out the alpha. The second property, the triangle inequality is always the most tricky to show. That's also true, and the reason is the same. The reason that the way you see it parallels the way you show the max norm. Right? infinity norm. It's a norm. Right? So we need to show that you have A, and then you get B. These are two matrices. You sum them up. We need to show that it's less or equal than the norm of A plus the norm of B. The way you do it, let's do it here. So we take the left hand side, we go to supreme over x, then you have this x plus 2x. I don't write the norm anymore. Then you use the triangular inequality of the norm in the numerator. So this is less or equal than the supremum over x, and then you have the norm of ax plus the norm of bx. You use the triangular inequality for the norm in the numerator, all divided by x. Then what you do, you write this function as the sum of the two ratios, right? So this is equal to of x of ax divided by x plus bx divided by x. And then it is as before. So when you take the maximum of the sum of the function, that is less or equal than the maximum of the first function plus the maximum of the second function. Okay? So this is less or equal to the supremum x plus here. So what we've used here is that this is always true. Functions f and g, you take the maximum of the sum that is less or equal. So the supremum of first plus the sum of the second. The reason for which you write supremum would be very simple. That's not the case. That's the way it is. So why do I bother with this matrix now? So norms are already abstract. Why speaking of these special norms for matrices? But the reason is that they appear quite a bit in many methods we study. For example, when they are related, for example, to the eigenvalues of the matrix. So, what is an example of an induced matrix norm? It is right, maximum eigenvalue of the matrix. So, if you take, let's write the definition. So if you take these two norms, the norm in the first space and the norm in the space, the domain space, you take them both to be the Euclidean norm, right? So the P norm will be equal to 2. Okay. So in that case, the induced matrix norm is confined by this equation, right? Because it is equal to the supremum over x, and the denominator is the square root of x transpose x. that's the norm of x. And the numerator, right, is the square root of vector transpose of the vector ax times ax, which is x transpose a transpose ax.
But you have the square root, so you put the square root altogether.
So you need to compute this maximum. And the result, not the fact, but the result says that now this is a rectangular matrix, but A transpose A is a square matrix. It is also symmetric, so it has eigenvalues. The result is the square root of the maximum eigenvalue of A transpose A. And as we will see later on, this is also this quantity is the what is called the spectral radius of the maximum singular value of the matrix. We'll see this notions a little bit later. Today. Okay. So you see that special case, very special case of an induced matrix norm, which corresponds to choose as the vector norms the Euclidean norm, the length of the vector, right? You obtain essentially the maximum eigenvalue of the matrix from A. For the geometric interpretation, we have to wait a little bit when we see the single value composition.
Excuse me.
Yes.
Why don't you have an m root and an n root? With just a square root instead.
This m is confusing, and also this n. So this just says that this is a norm and this is another norm. That's good. So it's completely abstract.
So it's not like a p norm.
No. It's a good question, right? Because
So what kind
you
of norm is
were
that?
confused that this is an m norm and this is the p equal to m norm and p equal to n norm. Right? But that's not what this means. But it could be. But we have not studied that norm. Let me go back, and but this is a good question. Let me go back and summarize a couple of things. We saw norms for vectors, and we made a general example of norms for vectors, which are these LP norms, which include the Euclidean norms, right? Which are length of the vector. Non, infinity, which are other interpretations. So these are a special class of well-used norms for vectors. Right? Then we discussed norms for matrices. As I said, matrices can be thought as big vectors. So any norms that you use for vectors, you can compute in the case of matrices. But that's not what I want to do here. So here I discuss induced matrix norms. Okay, so there are norms which are defined by first choosing two vector norms, one for the domain and one for the codomain of the linear transformation associated to my matrix. Okay? So I choose a norm in Rm, which is the space where my linear transformation maps to, and I choose a norm for the vector space, which is Rn, which is the domain of the linear transformation. This is what this notation means. So if I choose the m norm and the n norm to be Euclidean norms in the two different vector spaces of different dimensions, then this thing becomes the square root, etc. If I choose this to be p norms, it's more complicated. And in fact, at hand, I don't know what the result would be. So, for example, if you don't need to do that. Right? It's complicated. For example, we study this now. Supremum, number x. I can choose any two norms there. And this, as we proved before, is induced. Make this norm is a norm. It's fine. So I can choose, for example, in the denominator I could choose the one norm. The sum over I of x. Right? So one norm. And in the numerator I could choose also the one norm, or two norms. I guess let's choose also the one norm. You can do it as an exercise. I have no idea if this has an interpretation, if this can be sort of massaged. So you can move forward in the steps and obtain, the same way you have done here, a different expression for your proposal. Right? You can try. So here you take the sum of the absolute value of the component of AX, and the way you can write it, you take AI, the ith column, transpose X, absolute value. You take the sum. So you need to take the maximum over X, an arbitrary vector in n dimensions, of the sum of the scalar product between the column of the ith column of A and x, you sum, you form the numerator, and here you take the sum of the absolute value of the component of x. And then we can further massage this if we understand that there is some special x which makes this the maximum. Right? Possible. It seems possible. Actually, not sure, but well, if we are stuck, we can try to show a lower bound. But let me go a little further. This is just a digression. So, if we are smart enough, and if you are lucky, because sometimes it's not possible to derive an expression for this, you can find it. But so here, I don't have it, but for sure, you can try cases. So for example, we could choose x to be a standard coordinate. So x has all the components equal to 0 except 1, which is equal to 1. Right? So the denominator is 1, and the numerator will be equal to AI. Right? The norm, the L2 norm of the ith column. Right? So if I choose, what I'm saying, I'm saying something wrong. This is not correct. If I choose x to be EJ, I obtain AIJ. So for sure, this norm is greater or equal than the maximum element of the matrix. But I don't know. I don't know. This is left as an exercise, and we can discuss it later. So, but you can build many of these norms, and each of them can be a little problem. There are also examples of matrices, of norms of matrices, which are not induced, so which cannot be derived by this formula right now. This one. A very important example is what is called the Frobenius norm. So this is a fancy name for something which is just the Euclidean. Right? The Frobenius norm is the Euclidean norm of my matrix thought as a big vector. So it is the sum of the square of the elements, and you take the square root of sum. And here, for this definition, here you can show, you can argue that this we know is a norm. bigger norm. B matrix not as a big vector. The matrix not as a big vector, one norm as the other, so it's a norm. But this is not induced, so you cannot find two norms such that the continuous norm is equal to the maximum of the ratio of the image divided by the norm. Okay. So this is different from and we don't show that. Just the information. Okay. So that you cannot find the norm here and the norm here such that this is there are, it's useful to just, as a mental exercise, to see equivalent definition for this, for the Frobenius norm. You can also see it as the sum, you take the sum of the square norm of the columns, right, you sum them up, with the jth column, you sum them up, and then you take the square root, that's the same thing. Right? You just group these numbers column-wise. Likewise, you can see it as taking the sum of the square of the norms of the rows. So in this case, so if you compute this sum is equal to the square norm of the ith row. Instead, if you take this sum and you take it before the other, take the square of the length of the j column. So that's another way to interpret it. But you can also see that the root of the trace of A transpose B. That's another interesting way to think of the Frobenius norm. Right? So you form the matrix A transpose A, which is a square matrix. And the trace is the sum of the diagonal elements of that. Right? With the A transpose A, as we so A is n times n, so A transpose A is n times n. Right? So then if you look at the diagonal element, so J prime, so it will be equal to AJ transpose AJ. Right? Again, the trace of A transpose A is the sum of all these numbers. So you see that this is the same. So that the trace of A transpose A is the same as this. So that's a way to reason about these formulas. And similarly, the trace of A transpose gives you the same form. Questions? We can stop again for 10 minutes and we start this.